welcome back again. I thought we'd just start off with a quick recap of what we talked about in the last video. So I've got this this mass and spring system, and what I've done is I've drawn basically just a half an oscillation for this system. So you can imagine I've grabbed my mass and stretched the spring and set it oscillating. And I start looking at this system when my mass is at its maximum position, so plus A, the positive amplitude, and I'm just watching it move back through the equilibrium position, so this is equilibrium, towards the negative amplitude where the spring is compressed. Remember, spring constant is K in all cases. That's not changing because my third rule is intact. I'm looking at small oscillations, so there's no going beyond that elastic limit of the spring. And if you like, you can imagine that this is just going to go round and round like this. So this will just carry on repeating. So if you like, if we number these, so 1, 2, and 3, this will continue. It'll go 1, 2, 3, to 1, 2, 3, and so on. And what I want to just look at really quickly is what's happening to my position, velocity, and acceleration in these three cases, 1, 2, and 3. And if you like, you can think about this as it relates back to our graphs from last video. So maybe go back and check over those in relation to this. So what we're interested in is what's my position, what's my velocity, what's my acceleration. Obviously the easiest one to denote here are going to be positions because we can physically see them. That's going to be plus A. Here we're at equilibrium, so 0. Here we're at minus A. And what we want to look at is now the velocity in each of these positions. So if we sort of think about this physically, try and imagine what's going on here. When our mass, so let's go for position 1, when our mass is at its maximum position, that means that it's just at the point of turning round, so it's just here. If you like, it's a stationary point. So my V must be 0 here, and the same applies down here in position 3. This must just be at the point of turning round to go in the opposite direction, so V must also be 0 here. Equally, in the middle, we've got a sort of contrasting situation here where, depending on which way we're coming, let's imagine we're going from 1 to 2. This is going to be moving in this direction, but what velocity is it going to have? Let's think about this. Sorry, my bad. If we're going from 1 to 2, it will be moving in this direction. So what velocity is it going to have? Well, we can think of this as before this, before we get to this point at 2, there was a force acting on it in this direction, and that will be accelerating it. When it gets to the equilibrium position, we said by definition the equilibrium position means that our spring is at its natural length, so there is no force acting on it whatsoever. And once we continue past this point, once it moves along a little bit more, so once this spring is a bit more compressed in position 3, then the spring is, as I said, going to be compressed, so the force is going to be pushing this way and it's going to be decelerating the mass. So actually in the middle here, this is where I have my biggest velocity, so this will be Vmax. And I'll just put in brackets here that this is plus or minus, depending on which way we've come from. So if we're going in the direction 1, 2, 3, this is going to be negative. If we're coming back, if we're going 3, 2, 1, this is going to be the opposite. It's going to be positive. And again, we can go back at those graphs and look at that because we know, if I just quickly draw these graphs down here just to sort of give us an overarching idea. So I'll draw really roughly three axes, sorry, my position on the top. In this case, I'm starting from a maximum, so I'm actually starting off with a graph which is cosine, like that. Let's get rid of that one. So this is my x against t. V against t, as we said in the last video, is actually the gradient of this graph. So down here, v against t is going to be, well, let's think about this. It's the gradient. This gradient is decreasing here. So it is going to be a sine, but it's going to be an inverted sine, so it will look like that. And we can see here, as my position moves from positive A to negative amplitude, here my gradient is negative, which means my velocity is at a negative maximum, so minus Vmax. And likewise, up here, when I'm crossing the equilibrium position at 0, it's now on the positive, so my velocity is positive Vmax up here. So that's where that comes from. So at equilibrium position, sort of the thing to take from this is that V is maximised because there is no force opposing its motion, because it's at the equilibrium position. And finally, another easy one to look at. We know this relation. We know this relation from last time, that SHM is only satisfied when A is proportional to minus x. That means that here in position 1, I'm at the positive maximum position, which means I must be at the negative maximum acceleration. Okay, that means I have a maximised force pulling me back that way. Makes sense. Obviously at equilibrium position here, there is no force because the spring is relaxed. It's at its natural length, so that's 0. And down here, my spring is at full compression, so it's pushing backwards with a maximum acceleration. So that is, if you like, and again, it's another really popular exam question, just denote or just talk about the positions, velocities, accelerations at certain places along our spring, and that's what they look like through the lifetime of one oscillation or half an oscillation. But remember, it's symmetrical, so this works again in the opposite. Just remember to take care of these pluses and minuses on our Vmax in the middle in the equilibrium position. And while I'm here, I may as well just talk about, finally, I can draw a final graph for acceleration here. Sorry, this is really rough and ready, just off the top of my head while I think about it. Again, the easiest way to look at this is by remembering that A is always proportional to minus x. So whatever I've got here, I'm going to have the opposite for my acceleration. And it just so happens here that I've started off, x is actually a cosine, and that's allowed, that's absolutely fine. So the function looks something like that. Physically what this means is I've started my spring off by pulling it and releasing, whereas if I had yesterday, in the last video, sorry, we looked at a position function that was sine. So last video it was a sine 2 pi ft, and physically that just meant that instead of pulling and releasing, I actually started it off by pushing from equilibrium. So I flipped my mass, if you like. I just gave it some, starting off at this position, I gave it some initial impulse or something like that. So going back to here, A is always proportional to minus x, so if my initial function is this one up here, it's a cos, this one down here is going to be an inverted cos, it's going to be minus cos, so that will look something like that. Not the best cos I've ever drawn, but it will look something like that. Okay, so I said in the last video that we would start off, digressing a little bit, we'd start off by calculating a time period, because again that's another really popular question to ask. So they could say, considering this setup here, what is the time period? So given a spring with mass m and spring constant k, what is our time period? And to do that, we're going to have to consider our equation of motion again. So if you remember, our equation of motion comes from F equals ma. It's in motion, there is a force and therefore an acceleration, and the force is equal to Hooke's law minus kx. So we said that A was equal to minus k over mx. But we also said, another thing we said, was that A was equal to minus 2 pi ft squared x. And we got that by differentiating those graphs. And again, a little bit of differentiation there. Mathematicians, if you want to practice that, that was in the last video. So actually we've got two things which equal each other. So we can do a bit of equating these equations 1 and 2. What that'll do is it'll eliminate a, then I can cancel x, and that leaves me with just this function here. Sorry, just made a mistake here. That's 2 pi f, not 2 pi ft. And that will leave us with a function where the only variable, or sorry, not variable, the only unknown is frequency, and we know we can get time period from that. So let's do that then. If I equate equations 1 and 2, I'm going to get that minus k over mx is equal to minus 2 pi f squared x. That's lovely. X is cancel, minus 1's cancel. So now I'm left with this. Let's just tidy that up. K is 2 pi f squared. I obviously want to isolate my frequency, because that's where I'm going to get time period from in a minute. So let's square root both sides. That's going to give me root k over m is equal to 2 pi f. And now let's tidy up for f. So dividing both sides by 2 pi, frequency is 1 over 2 pi root k over m. And finally, what we're going to do is, we know that time period is the reciprocal of frequency. So doing that, that's going to give me that time period is equal to, now remember, these are all multiplied together, and obviously I've got some surd here. I can do the reciprocal of this in just the normal way, so I can take, if you like, imagine that's in brackets, I can do the reciprocal of this part and this part, and it will remain intact. That's absolutely fine. So that's going to give me 2 pi, and then I'm going to do the reciprocal of my surd, so that's going to be m over k. So this equation actually gives you the time period of any simple spring and mass setup in a frictionless sense. So there you go. That's that. And like I said, this comes up all the time. They'll ask you what spring constant you need if you want to make a clock that ticks in seconds given 100 gram mass or something like that. Yeah, you just sub in the numbers, rearrange for time period, and Bob's your uncle. Rearrange for spring constant in that case, Bob's your uncle. Okay, so another thing we're interested in then, if I go back up here, is what's happening to energy. And actually we want to look at the energetics of this system graphically. There are only two kinds of energy going on here. So if I just cut this out, and I'll steal that, copy it down there. There are only two kinds of energy really that are going on here in this system. It's quite a simple system. So obviously if we're at equilibrium position, that's where we said we have maximum velocity. And I'll just call that V. So at this point in the system, my mass is at equilibrium, so there are no forces acting on by the spring, which means there's no work being done by the spring at that instant in time. But it does have velocity, and that means that at this point I have some kinetic energy, which is half mv squared. Okay, so that's the most extreme, or one of the sort of extreme points going on in this graph. So let's just look at the other extreme then in terms of energy. Another extreme is when my mass is at some maxima in terms of position. So now my position is at, I'll just call this A. I'm not too interested in whether this is a positive or negative position. We'll see why in a minute. We know here, so considering energy again, we know at this point it's just turning round, so my V is 0. And if V is 0, I've got no kinetic energy. But I do have energy related to the spring. There is some work done by the spring here, and I'm going to call that elastic potential, so EP. And actually that's given by the equation half kx squared, so it is dependent on the spring constant. So now you can see why it's important that we don't overstretch the spring, because then we're changing those values and therefore changing the energy stored in the spring. So here, if you like, we just have potential energy, EK 0, up here EP is 0. And what we're actually interested in is what's going to go on sort of in between these two positions, because obviously at some intermediate point we're going to have a combination of energy. We're going to have a bit of potential energy because the spring will be doing work, moving our mass, but we'll also have a bit of kinetic energy because the mass will be moving. So we're going to have a sum of these two. So my total energy, E, is going to be equal to my potential energy, half kx squared, plus my kinetic energy, half mv squared. So that's my total energy. I will just say as an aside, this equation is derived by looking at the integral. So for you mathematicians, it's the integral of Hooke's law. So if you remember, just as an aside, Hooke's law, F is equal to minus kx, so the spring is doing some work, but as it's moving it through distance, so we can look at the work done by the spring, which is equal to Fs, but it's not, this is an average, if you like. If we want to do this for real, we want to look at how this changes, because we know the force is going to change. It's a variable. It's going to change as the spring changes. So really we want to look at f dx and do an integral between 2 points. And if you do that, the work done, depending on whether this is squashing or not, that we're either going from A to equilibrium or from minus A to equilibrium or whatever. So depending on the limits or the bounds of this integral, you'll find that the work done is going to be equal to k times the integral of x dx, which of course gives us half k x squared. Whether that's work taken from the system or given to the system depends on the bounds here. So just a little aside for the mathematicians there. Have a play with that yourself. A little bit of calculus. So this is my total energy, and actually what I want to know is, okay, I have this amount of energy at any instant in time, but what is the sort of total energy at any given instant? And we know quite conveniently what that is, because we know at either of the amplitudes, plus or minus A, so here, we know that all of the EK is being put into EP, and through conservation of energy that means that it can't have escaped the system, there's no friction or anything, we're assuming, and therefore it must be maximised and equal to that maximum amount. So what we can do is we can just sub in x is equal to plus or minus A, and going back to what I said earlier, I don't care whether this is plus or minus. You can see now, because this is x squared, the sign really makes no difference. So that's going to be equal to kx squared, but at the amplitudes that's going to be Ka squared. So this is my total energy, which is quite useful because that means if I look at any spring system, if I know the amplitude, I know exactly how much energy is stored in that system, which may be useful, again, thinking of exam questions. So this, if you like, is my final equation in terms of energy, and I'm just going to split this off into 3 bits. So this I'll just denote in red my kinetic energy, and in blue my potential energy, and I'll just leave in black total. So what we're often interested in doing is drawing a graph for this. So over the course of an oscillation, what does this look like? So this axis would be my energy in joules, this would be the position axis, so going from plus A to minus A, and we can draw each of these 3 parts on this graph, and the easiest one to go for is the total energy. There's no friction, conservation of energy is invoked, so it's got to be constant, we're not losing anything. So I will have some constant energy here, so black line, and this will be equal to E is half Ka squared. My potential energy is going to be maximized at either end because all the energy is stored in the spring, either in compression or in extension. So I'm going to actually intersect these 2 points at plus and minus A, and it goes as x squared, so it's going to be parabolic. I'll try my best to draw this correctly. Kind of there. If I if I just shift A across, you'll get my drift. There we go. And obviously that leaves us with kinetic energy. Going back to what we said right at the start of the video, we know that kinetic energy is maximum at the equilibrium position, so 0 here, which I'll just denote as EQ. We know it's maximized there, so it will go through this point. There is no potential energy, and we know V is 0 at either end of the amplitude, so it's going to be 0 there, so it's going to go through these points. And again, this, if you like, this is equal to the area under this graph subtracted by the area under the potential graph, and that's actually just going to give me an inverted parabola. And again, I'll try and draw this as best I can. I'll do. So this is how my energy evolves around each oscillation. So you can imagine here my oscillator is just going to be going back and forward along this line, and this is how the energy is going to evolve. And I should just say here, in case it's a bit misleading, this should touch that top axis, so I'll just correct that there. So that's how energy evolves as well. Okay. Right, this video took a bit longer than I thought. I got a bit sidetracked at the beginning, so I'll split this up into 2 videos. In the next video, as promised, I'll look at damping, and I'll also look at forced oscillations and resonance. So that's next up, and hopefully that'll be coming very soon. So thanks for watching, guys. See you later.